So, okay, yeah, let's start. Welcome to this session on global sensitivity analysis, and happy to see that I mean there is still energy to follow yet another virtual session on the screen. Yeah, and I will talk to you about tools that are available in Dinar to perform sensitivity analysis that are, I mean, okay, let's say a little bit special with respect to the, let's say, usual notion of sensitivity analysis. So then I do a quick introduction of the general concepts, and then I go in detail on the methodology that is implemented in Dynair, and which, in my opinion, is quite useful to tackle a number of questions that most of us sooner or later is having when I mean developing a model, checking its properties, and understand what's going on, and so on. So the general idea is that for doing a sensitivity analysis is that we want to understand what parameter, what assumption, what kind of model specification, and here I'm meaning, for example, types of preferences, or I mean, it could even be a model block. It's a very general notion of, let's say, model properties drives the behavior of your model, and how much a change in model factors, again, parameters, assumption, model specifications affects the behavior of a model. Okay, so that's, I think, a quite obvious notion of sensitivity analysis. So going to, let's say, macroeconomics, to DSG models. The first question that often arises is which parameters drive the uniqueness of solutions or indeterminacy and stable behavior. Okay, so for example, the Sharkan violation. Other questions may arise, so which and how parameters drive the sign and the shape of IRFs, impulse responses in a model. Which and how parameters drive theoretical moments of a model of model variables of interest, for example, autocovariances, cross-covariances among variables, and so on. Another question is, which kind of observables, let's say, affect the estimation of which parameter in particular, or vice versa, which parameters of the model mostly drive the fit of GDP versus, for example, inflation, and in particular, it might be interesting to analyze whether the right trade-offs, in the sense that it could be the case that data of inflation might like I don't know, parameter to be in a given region of, within the prior space, but maybe data of GDP would drive the same parameters in a different region. So clearly the estimation would make kind of a compromise, no? Would find probably something in the middle, and because there are these trade-offs. What is global sensitivity analysis? So in global sensitivity analysis, we consider a general computational model where X are the factors, so typically the model parameters. Okay, without loss of generality, we can imagine that those factors, parameters, are in 0, 1, but of course can be any kind of prior. And those distribution, and then, okay, there is an uncertainty, there is a space of uncertainty in the parameter. These are propagated to the model, and then you get you get your output. And the idea is to do so not to do so in a global way, in a sense that you want to really propagate the entire, let's say, uncertainty distribution in the input into a distribution in the output, and then infer the drivers of the behavior of the output. So you can elicit any kind of prior or any kind of distribution for the factors, could be continuous distribution, could even be discrete distributions. And you can have correlation structure, or typically you might also have your estimated models, and then you have a really a joint probability density distribution, and then you have a macro chain. You have a number of draws obtained by from a Markov chain Monte Carlo and from a metropolis. In whatever way you have your let's say inputs, your parameters, then okay, what do? Okay, you have a first draw, you propagate it through to the model, and you get okay, a first outcome in the output. You have a second draw, and then you get a second outcome in the output, and then a third draw, a third output, and so on and so forth. So you do this kind of Monte Carlo propagation, and to get let's say a Monte Carlo based empirical distribution of the probability, I mean of the outcomes, and that could be of course many different outputs of interest. So you might have for the same draws different distributions for the different outputs of your model. And so another definition of global sensitivity analysis can be that we want to study how the uncertainty in the output of a model can be apportioned to different sources of uncertainty in the model input. Okay, so this makes the notion of sensitivity analysis that I'm gonna, let's say, discuss here more related to the uncertainty. So the fact that we propagate uncertainty distribution via the model to get the uncertainty distribution of the output. This differentiates with what is the typical notion of sensitivity, which in the literature it can also be, let's say, defined as one at a time method. So one at a time method is a method where one factor, one parameter is perturbed in turn, keeping all the rest constant to the baseline. So this is essentially a derivative-based notion. Okay, so you have your central, your baseline point in the space of parameters, and you perturb one by one, okay, all parameters. This is of course valuable as well, because okay, we know how derivatives are useful in calibration, in estimation, identification, as discussed yesterday by Willy, inverse problem solving, and so on. But I mean, if you are interested in, I mean, in understanding, let's say, in tracing the effects in a space of uncertainty, which is not, let's say, in an epsilon, okay, in an infinitesimal, let's say, perturbation around a baseline, okay, this might be, I mean, might lack of power, okay, in tracing all the effects that you want to trace, especially if the models are nonlinear, of course, because if the model is linear, once you know the first derivative of the output versus the input, you know everything, okay? So clearly all these matters if the models are nonlinear. That's very important. And remember that even linearized DSG models in general are nonlinear in the deep parameters. So also a linearized DSG model, when you want to understand how the deep parameters affect your outputs, in that sense, the model remains nonlinear, okay? Because the reduced form solution of a linearized DSG model is actually a nonlinear mapping between the deep parameters and this reduced form solution. It is also true that, okay, for people, I mean, methodologies that, okay, develop the global sensitivity analysis, I mean, the trade-offs between one at a time and the global method is well known, but normally, I mean, majority of modelers, investigators consider maybe too complex or a bit, I mean, they don't have even the time to implement or to to go for these methods, and that's why I thought it would have been useful to plug these methods into Dynair, so to make them available, such that if you have a problem that might be tackled by these methods, you can just apply them instead of, reading the literature, implementing them, and so on. And okay, there are many global methods for sensitivity analysis, but I will focus on the most. This is probably one of the easiest one, but also quite effective, and so which is called Monte Carlo filtering. And so that would be the subject of essentially this session. So in general, global sensitivity analysis can surprise you, finding, for example, technical errors, because as soon as you start to perturb your model, check the propagation of things, etc., you might analyze that. You might find out that there are strange behavior for some parameter combinations, and this might be okay, or might just be due because of some maybe encoding error of the model or the equations. It can cause model relevance in the sense that if you have a lot of parameters, but in the end what counts are only a couple of them, maybe you can prune your model for the objective of and restrict maybe some blocks, okay, to tackle, to make it fit for purpose of your variables of interest. It can help identifying critical regions in the space of inputs, like, for example, instabilities or violations of Blanchard condition. It can help in estimation and calibration. It can help in establishing priorities for research, in the sense that it measures how much the ignorance on parts, on some parameters is more relevant for the precision in your outcomes, and then maybe you want to invest more in getting better information about the specific parameters with respect to others. And very important, because especially in economic models, but not only, those models are also used for policy advice. Sensitivity analysis can anticipate and prepare against falsification of the analysis, in the sense that models sometimes are also used really in policy debate, even on newspapers. They are criticized. Sometimes this happened. Okay, there has been a lot of critique of models, for example, after the financial crisis, but also environmental models in all the debate regarding global warming. There are probably still debates that how much the assumptions impact the projections, how much the model specification drives the results, and then the policy advice. Clearly, a sensitivity analysis can be helpful, because you can substantiate the results better. You can show how hypotheses matter, and then that can be very, very, very important. Okay, so that's to give a general context on why this notion of global sensitivity analysis can be useful, and then I describe the methodology that is implemented in Dynair, and with a number of applications. In the discussion, let's say, group, I uploaded also some exercises, if you like, you want to practice, and I will also show on the fly some examples as well. And then in the Q&A, we can either review the exercises or respond to any questions. As in the other Q&A sessions. Also, please interrupt me if you have questions or if something is unclear. So then I move to the next presentation. To the next, if I find it. I guess you see the new presentation. Monte Carlo filtering or regional sensitivity analysis. These are, let's say, two names of the same object. Monte Carlo filtering is one useful method for doing global sensitivity analysis that is based on a simple type of algorithm. So first, you need to define, let's say, a definition of behavior, which can be loose criteria, like a set of constraints, thresholds, ceilings, time bounds, based on available information of the system you want to model, based on, I mean, your preferences, etc. So, for example, a typical classification for a DSG model could be, you know, I want a model that doesn't violate Black-Sharp conditions. Other situation, I want a model where the response of GDP to I don't know, a cost push shock, I don't know, stays in a given range of values, or I mean, it goes to zero fast or less fast. I mean, whatever kind of criteria you want to look for. And then, based on this qualitative definition of behavior, you define a classification of the model outputs. Okay, so we have already discussed before. So then we are always, so here the setup is that a Monte Carlo setup. So we have a number of draws out of the distribution of the parameters. You have propagated it through the model, so you have a number of draws of your output, and then you classify the output as being behavior or non-behavior according on whether the model output lies within the constraint that you have defined in the first step. In practice, you have a Monte Carlo sample of size n of all your input factors. You propagate through the model, and then this big N sample will have two subsamples, small n and small m, where there will be m draws which are behavioral, so they stay within your thresholds and criteria, and n will stay outside those so they are non-behavioral. So then this classification, which is based on the behavior on the output, is is projected again onto the input, no? Because then for each input, okay, you have the input values associated to the behavior and the input value associated to the non-behavior, okay? Because in the end, what we are interested in is which among those xi's is mostly driving the behavior of the model. So you need to, let's say, backward, okay, invert the criterion that you have set for your output onto the inputs. Okay, so this is a typically an inverse problem, and yet another example of an inverse problem. So this depicts the main features of this type of an inverse problem, because let's say the behavioral criteria on the output are very clear. No, you have a clear threshold, you have clear, ideas of what you want to do. But the model is non-linear, so when you backward propagate on the inputs, then those boundaries are not so neat. There can be nonlinearities, interaction, or whatever complicated. So it is not trivial to map, okay, what's driving the behavior out of the entire input parameter distribution. So how does Monte Carlo filtering try to trace these drivers of the behavior? Is by doing a very simple statistical testing on the two samples that are obtaining by filtering, okay, the Monte Carlo draws according to the behavior and non-behavior. So we apply the Kolmogorov-Smirnov two-sample test for each parameter, for each factor. So the null hypothesis is that the distribution of the parameters under the behavior and non-behavior are identical. And the alternative test is that the two distributions are actually different. Small f is probability density, whereas big F is the cumulative probability density. So this test is based on computing a test statistics, which is, let's say, the distance between the empirical cumulative density distribution under the behavior and the non-behavior, and where clearly we index the cumulative, let's say, empirical distribution by the actual size of the two samples, because clearly the two samples might not be in general, they are of different size, of course. So this is how it is done in practice. So, so assume that the blue line is the empirical cumulative density distribution of the behavioral draws associated, so of the X associated to the behavioral draws, and the red is the cumulative density distribution of the draws of X associated to the non-behavior. The D statistic is the max of the distance, of the vertical distance between the two lines. So then, as in any statistical testing, so the question is, at what significant level alpha does the computed value of D, the statistics, determine the rejection of H0, of the null hypothesis? And the null hypothesis is that the distribution red and the distribution blue are the same. Okay, so their difference is just because of, let's say, small sample, or I mean, just randomness, but not the kind of structure. So the two distributions are not significantly different. And then the importance of each parameter is inversely related to the probability. So what's the idea behind this? Is that if the distribution of X associated to behavior is strongly different with respect to the distribution of F associated to the non-behavior, this is an indication that X might actually drive the behavior. Now, assume that the blue distribution would be completely biased on the right. So the cumulative density would be really something that is tilted on the right. And the cumulative density of the right is completely tilted on the left. This is suggesting that if you raise the value of X, okay, so if you get large numbers of X, you are much likely to go towards the behavior of the model. Okay, so then since the significance level is inversely proportional to having the null hypothesis, so which means that it is inversely proportional to having the two distribution very different. So the importance of each parameter is inversely related to this probability. So then what we do for even level alpha, there is a critical level D, which depends also on the size of the two samples. And then if the distance, so the maximum distance is bigger than the critical level for each alpha, then H0 is rejected. So then the two distributions are significantly different, and then that parameter is flagged as important in driving the behavior of your model. Let me reiterate a bit, because, okay, that's probably the end of a kind of a theoretical, let's say, thinking, and the rest is really very practical. So let me make a slightly different plot, which is yet another example of a possible shape that you see. So first you need to start, what maybe you need to start learning is to learn in terms of cumulative density and not of probability density. So the blue is again the cumulative density of a parameter 1 under the behavior of the model, and the red is the cumulative density of the same parameter under the non-behavior, and the yellow is the prior. Okay, so in this case the prior was a uniform, no, because a cumulative distribution of a uniform is just a straight line between 0 and 1. So what does this mean? Okay, for sure, I mean, the Smirnov statistics in this case will tell that the two distributions are different. But most importantly, what you would like to do also to be operational. So you are interested to know that X1 is important in driving the behavior, but this tells something more. This also tells you which values, okay, where you have to move X1 to go to the behavior, and how you have to move. So when you know that the probability density is the derivative of the cumulative. Okay, so then when the cumulative is steeper, the density is larger. So this means that this plot says that the density of values of X1 under the behavior is large on the right-hand side of this plot, whereas the density of parameters under the non-behavior is dense on the left-hand side of this plot. So then intuitively, so this type of plot says you that if the blue line, let's say, is curved toward the right, you have to pick large values of the parameter to get the behavior, and vice versa. So then this approach not only tells which parameters drive the behavior, but also for which values you are more likely to go towards the behavior. And now I show you a number of, we discuss in detail a number of typical questions that can be addressed with the sensitivity analysis, and where essentially we need to learn how to interpret those types of graphs and let's say the output provided by Dynair. So let's start with the first thing you need to have. Typically, to run a simulation, you want to have that the model is solvable, so you have a unique solution. So Blanchard-Kahn condition checks for 3 situations. So if the number of forward-looking variables is equal to the number of eigenvalues bigger than 1, you have a unique saddle path solution. If the number of forward-looking variables is bigger than the number of explosive eigenvalues, you have indeterminacy. If the number of forward-looking variables is smaller than the number of explosive eigenvalues, you have an explosive solution. And this also provides a nice, what I said at the beginning, that you need to have a classification. This provides a nice classification. So whether there is a unique, indeterminacy, explosive, or other situations. So let's pick a super simple model, a Phillips curve model. Okay, so in the end, the only kind of structural equation in this model is the last one. So you have, this is a hybrid Phillips curve, so current inflation depends, on the expected inflation, but there are omega, let's say, so there is a price indexation or a share of firms that don't update the price in each period. So so then the expected inflation only waits for 1 minus omega, and there is an indexation that waits for omega, and then there is a Phillips curve slope that multiplies the output gap, and then there is a cost push shock. In this case, we modeled the rest of the variables as exogenous patterns. So we have GDP, and GDP is just decomposed in a cycle and a trend. The trend is a random walk process, and the cycle is just an AR2 process. An AR2 process is parameterized in terms of period and amplitude. So to ensure so to ensure that we don't have persistent oscillations. So this model can be, so no, sorry, okay, period and amplitude. Okay, so so this model, so the uniqueness of the solution of this model can be derived analytically. I don't make the proof, but the analytical result says that there is a unique saddle path if omega is bigger than 0.5. So there must be at least 50% of firms that are backward looking to provide a unique solution for this simple model. So then assume that we are lazy and or we don't know how to solve this uniqueness problem with paper and pen. Okay, so then we do Monte Carlo. So we pick, we don't know in general which parameters could affect the things. So we say that the candidates can be omega, amplitude, and period, and we draw them in a Monte Carlo fashion and check the Blanchard-Camp condition. And then after checking, we apply the Kolmogorov-Smirnov test to check whether it does something. So in this case, what you get, clearly the parameters of the cycle of the AR2 don't matter at all for the uniqueness of the solution. So in fact, you see that the red and the blue lines, so the two cumulative distributions for the behavior and non-behavior of the parameters of the R2 are totally identical. So those two parameters are not associated to the violation. Whereas for omega, there is a very extreme, let's say, split of the two distributions, because you see that the behavioral, let's say, values are only present above 0.5, and the non-behavioral are present between 0 and 0.5. So the Monte Carlo testing and the Monte Carlo analysis exactly replicates the analytical result. So the analytical result is that omega is bigger than 0.5, and here you get exactly the same, because you see that if omega is bigger than 0.5, there is not one red let's say, point remaining, okay, because the cumulative distribution reaches 1 when omega is 0.5. So in this way, we replicated the analytical results not using paper and pen, but using this methodology. Let's complicate a bit more the model. So instead of having a unique parameter, we allow for having two separate ones, so an omega backward and an omega forward parameter. So we have, for our Monte Carlo analysis, okay, first, again, also in this case, we have an analytical solution, and in this case, the analytical solution prescribes that the sum of the two coefficients must be smaller than 1. Again, let's assume that we don't know how to do the paper and pen proof of this uniqueness condition, and so we apply the same methodology. Again, a priori, we might have whatever number of parameters candidate to drive the uniqueness of the solution. And the Kolmogorov-Smirnov and those testing, the Monte Carlo filtering says again that the two parameters of the AR2 are not really associated to the behavior, because the red and the blue cumulative distribution are one on the top of the other. Vice versa, there is a clear, split between the two distributions for omega f and omega b. And what does this tell? So, so now we see that the behavioral lines are tilted towards the left, which says that if you want to, let's say, try out some parameter combination to get a unique solution, the thing that you should do, you should lower the value of those two parameters. And in fact, this is correct, okay? It's not really the analytical, let's say, expression here, but since the sum of the two guys has an upper bound, okay, so must be smaller than 1, clearly if you lower each of the two numbers, you are more likely that their sum is more than 1. And so that's an operational, let's say, suggestion that tells you that if you lower those two numbers, you are more likely to get a unique solution. And here we do one last step, because there is an additional possible check that you can do out of your Monte Carlo sample to go a little bit further. So what you can do, you can also check for covariances in the blue or red samples. Okay, so here we analyzed only the cumulative distribution, but there are also covariance structure within those two filtered samples. So if you do so, you identify that actually, and that's actually the typical Dynar output. So on the diagonal, you have the same plots that we showed before, but off diagonal, we show the bidimensional projection of the two Monte Carlo samples for behavior and non-behavior for each couple of parameters. And in this case, you see that the behavioral set is exactly in the lower triangular part of the square. And in fact, this formula, omega b plus omega f smaller than 1, is exactly the portion of space below this line. Okay, so also in this case, combining the univariate and the bivariate analysis, we were able to derive, let's say, the equivalent of the analytical, let's say, expression for the uniqueness of the solution for these simple models. And that's also the typical output of Dynar. So what the Dynar does, it first checks for, let's say, the Kolmogorov-Smirnov. And then it plots only the parameters which are significant. So you don't want to have zillions of plots for parameters where the two distribution are one on the top of the other, there's nothing to tell. No? So then we started from 4 parameters, and the typical output of Dynar is that it shows only the parameters that are identified to be relevant, also to make your, let's say, visual inspection faster and easier. You can also go a bit deeper. So when you are in the red, okay, is it indeterminacy or explosive? So then, okay, you can also see that you can then trace indeterminacy, and then you see that in the triangle of red dots, this half triangle only is associated to indeterminacy, whereas okay, then you need to be careful about the names. So here there is omega f on the x and omega b on the y. Then since the Dynar ranks by importance, it is clear that omega b is the highest Smirnov statistics, so it is put at the top. So then, okay, they appear the same, but they actually, one is the transpose of the others. Okay, you need to be a bit okay, a bit flexible. So in fact, you should combine this has omega b on the x and omega f on the y. So this is this triangle. And then you combine this with this, where again you have omega b on the x and omega f on the y. So you say that this triangle here and this triangle here together, they make up the entire half triangle of the original space. So which means that when there is no saddle path, for 50% of the cases you have indeterminacy, and for 50% of the cases you have explosive solutions. So methodologically, it is as simple as this. So you filter the samples, you check, you do these simple checks about the Smirnov statistics and the correlation. You get those plots, and then okay, it's also a matter to being capable to interpret in a proper way those plots. Clearly, the models are not as simple, and we want to be sure that the methodology works for, let's say, true models with the desired complexity. So We can go a little bit more complex. We can take the Lubick-Schorfeide model 2005, which has 12 parameters, and do the same Blanchard-Kahn analysis. So this model is a small open economy model with featuring an IS curve where alpha is the degree of openness, tau is the intertemporal elasticity of substitution, Q is terms of trade, Y star is the rest of the world GDP, Z is the productivity shock, I think. This is the Phillips curve, which again depends also on the openness, and kappa is then pins down the slope of the Phillips curve. This is the output gap. Domestic price depends on the exchange rate. The delta is the growth of the exchange rate in terms of trade and the rest of the world prices. There is domestic Taylor rule, domestic monetary policy, which also allows for pegging the foreign currency. So it also has a weight to exchange rate, not only to the inflation and the output gap. And then there are exogenous processes for the terms of trade, for the rest of the world GDP, for the rest of the world inflation, and for the technology. This model has been estimated with these priors. And we want to analyze the uniqueness. So if there are portions of the space that don't provide unique solution. So what matters, of course, for the Blanchard-Kahn is only the parameters, not the variance of the shocks. Anyhow, we have 12 parameters, potentially candidates to drive a possible violation of the Blanchard-Kahn condition. You run the things, and out of the 12 parameters, Dinar provides you this kind of plot. So it pins down that there are only 2 parameters that are associated to the violation of Blanchard-Kahn, and the parameters are psi1 and psi3. What are psi1 and psi3? Psi1 and psi3 are the coefficients of the Taylor rule versus inflation and versus the exchange rate. So, and what does it also tell? It tells that most of the time Blanchard-Kahn are okay, but as soon as psi is small and or psi3 is small, you may have a violation. So we know that there is a Taylor principle, okay? Typically, the Taylor principle says that there is a unique solution, so there is no indeterminacy if psi1 is bigger than 1, okay? Here, the thing is actually a bit more general, because what this says is that you see that you might not have violation. You see that the blue cumulative distribution arrives to 0. So you can have psi1 numbers which are really almost 0, and still it is possible to have a unique saddle path. How is it possible? Because in this model we also have a response to the exchange rate. And then if so, if the exchange rate response is sufficiently large, you can also have psi1 that violates the Taylor principle. And in particular, you see that actually the violation is a region below this straight line, or vice versa. The Taylor rule provides unique solution for all the parameter combination above this straight line. What is this straight line? So this is 1. This number here is 1, is between 0 and 2, and also here is 1 because the domain of psi3 is 0, 2, so it's in the middle. So what does this? It says that psi1 plus psi3 has to be bigger than 1. So this says that there is a generalized Taylor principle for exchange rate targeting that says that you don't have indeterminacy if the sum of the weight to inflation and the weight to the exchange rate is bigger than 1. Okay, so there is always the one threshold, but in this case, it is the sum of the two guys and not only this one that may drive the unique of solution, the uniqueness of solution. Okay, you can also check. So this is unique saddle path and no unique. Then if you want to trace indeterminacy, the result is the same. So in this case, we don't have explosive solutions. Okay, so whatever can go wrong in here is just indeterminacy. Okay, so this is one big class of problems that you can tackle quite effectively with Monte Carlo filtering. Okay, then you can okay, one type of generalization is that in this case we have draws, we have taken our Monte Carlo draws from the prior, actually, in this case from the prior range. So we know that, okay, here there are prior densities that are gamma, so there should be kind of denser. They should be denser, let's say, in the middle and less dense in the, let's say, when you go to the tails of the prior distribution. In this case, okay, there is kind of a prior, a prior range, no, associated to the density, and in this case we have sampled uniformly in the range of values associated to each prior distribution. This allowed us to, really sample densely also the corners and clearly, show those let's say, these boundaries for the Blanchard-Kahn violation. You might also want, there are cases where you find yourself in a specific point in the parameter space. For example, you are optimizing, you are estimating your model, and at some point, the estimation stops, so the optimizer stops, but you don't find a maximum, but you find that you are actually at the boundary of some violation. You are on a cliff, you don't understand what's happening, maybe you have 40, 50 parameters, and you don't know how to get out of this region. So another type of so then you can change the way you draw your sample. Instead of using the prior, you are in a critical point in the parameter space, and then you want to draw in a neighborhood of this parameter. Okay, but then the objective might be the same. So I show just examples of let's say a real model with a lot of parameters, where at some point you go dangerously near to something wrong happening, and then you might get similar things of plots, but where importantly there is also extra information of the points where you are. So the green dot is where you started from, and then you draw things, let's say, in the neighborhood of this, and they see what's happening. So in this case, it is clear that this alpha parameter is probably an issue. And then maybe it's better to keep it smaller, maybe to get out of some trap or some possible cliff during an estimation. This is again when you compare the unique solution versus everything else. Then explosive solutions okay, are associated to other kinds of parameters. In particular, okay, this is, for example, a parameter triggering the stability of depth. Okay, it's a depth stabilization rule. If the parameter is too small, you might have explosive solutions, for example. But in particular, there can be indeterminacy if this alpha parameter is high. But for further higher values of this parameter alpha, there is also inability to find a solution, because in fact there are other situations where you cannot find a solution. Is because, for example, the steady state is not solvable. You get complex numbers, or there are other things. So then, in fact, on top of this, is also useful to tell you that not necessarily you can even evaluate the eigenvalues for every parameter combination, because there are parameter combinations for which the steady state doesn't exist. I don't know, investment becomes negative or whatever, something goes wrong. And so there is also this other situation. Anyhow, that just to say that this method can pin down, I mean, typically critical situations, and the way to escape. So in this case, it was to lower this alpha. So there are a number of options you can set. Typically, you want to say the number of draws. The default sampler is is quasi Monte Carlo sampler. Then if you want to draw from the prior, you set p prior equal to 1. If you want to, on top, sample uniformly from prior ranges, as we did here, you set p prior 1 and prior range 1, and that's the default. Okay, Morris is another method, but okay, we don't focus on this. Vice versa, if you have already an estimated model and you want to analyze what's happening around using the posterior draws, you set p post equal to 0, and this overrides everything else, because once you have p post equal to 1, you just fetch metropolis draws. If you want to sample in the neighborhood of a specific parameter point in the parameter space, you have to trigger this neighborhood width, which is a real number. And the idea is that assume that you have a parameter array, a parameter vector, which you have stored in a quote-unquote mod file, then the interval is 1 plus minus delta. Okay, so it's a relative deviation. Then the other important thing is about the p-value, no? Because we want that dynaire only plots the parameters that are relevant. So we want to set a threshold. So then, which means that the default is that the p-value for the Kolmogorov Smirnov is 001. So we only plot parameters for which the null hypothesis is rejected at a p-value smaller than 001. And also, when we compute the correlations, we also consider correlations that are significantly large at a p-value smaller than 001. Yeah. So, and of course, another important thing is that if your model is non-stationary, so if there are unit roots, remember that linear may have different notation. So by default, unit root is considered as an explosive root. If you want to consider in estimation, for example, by default, we estimate stationary model in linear. But in fact, if you have a model which is non-stationary, you have also to tell this to linear. So these are the situation of the syntax. So there is a command, linear sensitivity analysis. Prior range equal to 0 means that so the default is p prior 1, but you set it to 0. So this then draws from the true priors and not from uniform intervals. Okay, you can also give a lot of options of estimation, like no display, graph format, the number of draws. Load stability 0 means that okay, you check let's say the stability for the new draws. In some cases, you may want to do further analysis after having done already the stability. In principle, you can have load stab 1 load, so you load already a previous sample and then you do something more with this. Vice versa, if you want to draw some in the neighborhood of something, you may apply this, for example, number 01, and then you need to declare a mod file. So a mod file needs not to be actually a true mod file. It's just a way to store an array an array of numbers for the parameters around which you want to sample, because there's something strange around that value that you want to understand. A second big class of questions that you may want to tackle with Monte Carlo filtering is calibration. Typical way of calibrating is some sort of IRF matching or moment matching. Loose notions of these, whereas really, I mean, we'll talk about proper moment matching also in this summer school. Anyhow, so you want to restrict you want to restrict impulse response, okay, in a given shape. You might even want to check for you may want to avoid a lot of sign changes. So maybe we don't like to have too many oscillations in IRFs, and we want to target or we want to target a benchmark model. So for model comparison. Moment calibration, we want to match key properties in the data, auto or cross correlation or sign restrictions. So we can trigger this to add an extra block to the dinar code. So you can add an IRF calibration block where you might or might not want relative IRF. Typically, relative IRF is handy if you want to let's say reason in terms of multiplier. Okay, so relative IRF is so dinar computes relative IRFs in percentage points, which means that a multiplier 1 turns out into a 100 number. Okay, so for example, for the Rubik-Schurfeide model, we might want to have. Okay, so this is okay. Okay, so this is the response of the GDP versus the foreign GDP shock, rest of the world GDP shock. Okay, these are the first 4 periods of the RF, and these are just, let's say, some, okay, so the dotted lines, the dotted thick lines show the, let's say, the max and min out of the prior Monte Carlo sample, and then those thin lines show the deciles, and the thick line is the median. Okay, so you see that these IRF can have, I mean, a huge range, can even change the sign, and assume that we want to target to rule out too big responses in absolute value, and this is depicted by the blue area here. So how do we do it? So GDP in periods 1 to 4 after a rest of the world shock must be between -50-50 in relative terms. Vice versa, for the interest rate response to the same shock, we want it to be small. So you see that the tail of the distribution is very fat. There are really huge numbers out of this. We want to limit our behavior to be restricted to relatively small values. So what we say that, okay, we want that, especially in the long term, so we want the interest rate, essentially the interest rate response is near to 0 after 5 years of the shock. Okay, so we want to restrict the interest rate response to, I mean, as I said, to go back to equilibrium fast. And then, okay, there is also another notion, because then, okay, you can give restrictions with an array here, or you can give a restriction one by one, let's say one restriction by row. So the logic here is that within each row, if there is an array here, it is a logical OR, which means that I am happy if at least in 1 out of the 4 periods, the GDP response is within the prescribed threshold. But across rows, there is a logical AND, which means that we want to catch simultaneously all the different criteria that we want. So then this thing says that we want to have, for each and every period between 21 and 4, the interest rate to be very small. And at the same time, to have the GDP to respond, let's say, in a moderate way in whatever of the first 4 periods. Then this is what you get from Diner. So you see that, okay, to get GDP into the prescribed region, you need to have in particular tau to be high. Okay, tau is the inverse of the intertemporal elasticity. And here there's a last, let's say, important element for the interpretation of these plots. So you see that in the off-diagonal, in principle, we should have the same, let's say, type of plot, just transposed, but the plots are actually different. Why? Because on the lower triangular part, we plot the blue and the red on top of the blue. Okay, and we do vice versa on the upper triangular. And in particular, what I like to look is always at the low triangular, because what does this tell? Since, I mean, in general, there are many parameters, so as soon as there are more than 2, there can be a lot of interaction. So then you are never so lucky to get this nice, okay, separation between red and blue. Okay, there are always interaction, there are always many factors simultaneously. So, I mean, there are overlaps. Then, why I like the lower triangular? Because it says that if there is blue, so assume that the blue is the, I don't know, the sea, and the red are the clouds. Okay, so you want to avoid the red, and there are interactions. If in the Monte Carlo analysis, you see that there is a blue that you can visualize, okay, that are not covered by the red dots, it means that if you move, okay, the parameters in this region, you are sure that you go into the behavior, whatever other interaction may do. Okay, so then typically my way of looking at this plot is that, okay, you look at the triangles, but also you look at the lower triangular and see whether you see clearly portions of the space that are blue. And this suggests that you should move there to go for the desired behavior. If you go to interest rate versus the same shock, the plot is different. There are still blue regions visible below the clouds, let's say. So also here, I mean, you can find a combination of parameters that provide the desired behavior. With a very similar syntax and similar approach, you can make this moment calibration or moment matching. So in this case, you want to target some autocorrelation or cross-correlation. In this case, you have the autocorrelation, GDP onto itself in the first 4 periods. And you want it to be positive. So, and then if you want to be positive, there is also a shortcut. You just write a plus. Okay? And this is, as before, there is the OR logic. So what I'm saying here, you are happy if at least in one of the first 4 legs, there is the positive correlation. If you want the AND logic, then you have to do several rows at the same time. So this means that you want to have that the cross correlation between GDP and interest rate, between -2 and +2 legs, you want them to be negative. Okay, and also you want to have a negative link between GDP and inflation. From legs -4 +4. So this means that you want to match simultaneously these conditions, and these conditions. Okay, similar to before, you can run the sensitivity toolkit, and then this is what you get. So for example, this is how you can get the negative correlation between GDP and inflation in the first, in the legs -4 +4. And also here there are, I mean, 3 parameters mostly identified, but in particular, so rho A is the persistence of the technology. rho r is the inertia of the Taylor rule. You see that here is a bit more difficult because you see that the red cloud covers a large space of the blue, but again, if you combine if you combine large rho A with the small rho r, so if you pick some numbers in this region, you get what you like in the moments. Similarly to GDP versus okay, so then you might go in each and every leg. So y-opt versus y-opt leg 1. So this is much easier. Clearly, I mean, these are 9 moments overall with restriction. So the bigger the amount of restriction, the more difficult it will be to find the blue. To dive into the blue. For each individual, it would be much easier. And similarly for GDP versus interest rate, again, there is you need to have a high persistency mostly to go there. Yeah, and that's it. And then, okay, in the end, if you want to match everything simultaneously, as I said, the more restriction, the more difficult. And so you see that, I mean, just let's say using 2 parameters as trigger is very difficult, but this is suggested that if you combine larger rho A, lower rho IS, and maybe also lower rho R, okay, if you do some combination of these parameters, then you're likely to go in a situation where you are matching all your criteria. Okay, then clearly, I mean, you may want to go for more formal optimization things, but this already provides you quite a lot of information about which drives what and in which direction. And now I go on to a more, possibly more interesting application of these IRF things, which is, for example, the government spending multiplier. Okay, and here I'm just telling a story about a paper I wrote with my colleagues, Werner Röger and Jan Intel of DG ECFIN in Brussels, using the Quest model, which is DG ECFIN's DSG model, one of the 2 DSG models of the Commission. This, in particular, the Quest model is the most, let's say, the older one, and it's the one that is used for doing many, let's say, policy simulations for the European Commission. And okay, we made an estimated version of the model, of the Quest 3 model, and we introduced the rule of thumb consumer. And there was the Gali paper, no, at the time, saying that I mean it's sufficient to have a moderate amount of rule of thumb consumer to get crowding in of aggregate consumption. Then, okay, we estimated the model, we ran the RF, and actually we still got crowding out. And then, okay, we were a bit puzzled. How come? Maybe there is a mistake, there is an error somewhere in the model, or maybe there is something different. So we started to do this Monte Carlo analysis. Okay, so in this plot we see the prior. We see the prior distribution of the response of consumption and of the 2 households consumption with respect to the government spending shock. So we see that in the prior distribution of this model, indeed, there can be situations where also aggregate consumption has a positive response, but actually still the density remains rather, let's say, strongly tilted towards crowding out of consumption. Now, if we go towards the 2 individual households, we see that for the rule of thumb consumers, actually the prior distribution is not systematically positive, but I mean, it is kind of half and half. There can still be crowding out of consumption also for the rule of thumb consumers, whereas the Ricardian is usually always crowd out after this kind of shock. Then we made a Monte Carlo filtering analysis to target the behavior of Gali. So we want to have crowding in. And there was this type of plot, a number of parameters were identified, and in particular the top The top one is gamma. Gamma is a Rottenberg adjustment cost, in particular a Rottenberg adjustment cost for labor demand. So in the Quest model, the Quest model is a rather rich model. It has a lot of frictions, nominal real rigidities, but also a number of frictions also in the firm side. And in particular, we have labor demand adjustment costs, which, by the way, are not present in the Gali paper. And what this plot says that actually to get crowding in of consumption, we need to go small with this labor demand adjustment cost. And in particular, you see that, I mean, already with the gamma bigger than 0.5, essentially, the cumulative distribution is almost entirely to 1. So it's very difficult to find crowding in if gamma L is bigger than 0.5. So what we did, following this result, we redid. So we checked what happened by freezing gamma L to 0. And then freezing gamma L to 0 and running again the prior, let's say, propagation of all the other model parameter priors onto this IRF, we see that now the prior IRF is almost all the time for crowding in. We have that the Ricardian, the non-Ricardians are almost always crowding in, and so the non-Ricardians are negative, and for some peculiar parameter combination can also crowd in. So this means that this shows very nicely, okay, how, let's say, sometimes even the prior itself drives the output, in a sense that if we would estimate the model with this rigidity equal to 0, gamma L equal to 0, and then don't look at the prior, but just look at the posterior, okay, we would see that the posterior provides crowding in of consumption, and then we would conclude that our estimation has estimated crowding in with a given degree of a given amount of rule of thumb consumer. But this is actually more driven by the prior, in the sense that if you allow also other parameters to be estimated, so the prior actually changes its shape, and then the result might change. So this also shows how your prior assumptions might also drive the results in a way, and how maybe extensions of models, and then okay, you pick a specification from a prominent paper, but then in your model you add some extra feature, you might not let's say recover the previous results, because the new features that you have in your model actually may change, let's say, the situation. And if this parameter actually, so then removing the parameter is also, I mean, identified, it helps to fit the data. And so then this means that, I mean, if you cannot get rid of this rigidity because of empirical reasons, because of explaining the data better, this means that it's not obvious to get crowding in of consumption even in the presence of rule of thumb consumers. And so this is how, I mean, examples can be brought into a more, let's say, meaningful policy questions. I pick some water. Sorry. Okay, so one last possible setting where it can be interesting to perform this kind of global sensitivity analysis is vis-a-vis observables and estimation. So how do parameters adjust to fit many, the multiple sets of observables that we want to fit, on which we want to take the model? Would they change by adding, removing observables? So would the posterior of a parameter, is it likely to change adding or removing observables? And are there trade-offs? As I said, are different observables driving the same parameter into different directions? Okay, so there are also possible other more, let's say, rigorous and formal approaches to do this. But this is also a problem that can be tackled in Monte Carlo. And okay, the advantage of this is that, okay, sometimes, okay, you might not pick the full picture, but the nice thing in this is that, okay, you do it as typical in global sensitivity analysis, you do, let's say, everything in one shot. So everything is put together at the same time, and then you trace the signal. So instead of doing, for example, different estimations for different sets of observables, which is time consuming, with this approach, you can have a fairly nice preview relatively fast, okay? And so I think it can also be useful. And and then this is a type of problem that again can be framed in terms of Monte Carlo filtering. So again, you need to have a Monte Carlo sample. You might sample again from the prior. So before starting an estimation, you might want to have a preview of what might go on, or you might have your estimation done, but still you want to understand what's happening within, let's say, the posterior, okay, relative to the fit of the various variables. So how do we do this? So then the filtering criterion, so the behavior criterion, can be the root mean square error or the R square. So among the many other things that you get out of Dynar when you estimate, you can have, let's say, subdraws of k-step ahead predictions of the model. So then we can pick the one-step ahead prediction of the model for each of the observed series and filter the best. So, which also means that since there are n observables, you have n different filtering rules. So then for each of the observable, you define the behavior as the best 10%, so the smallest 10% root mean square errors out of the entire Monte Carlo sample, and no behavior otherwise. So which means that for each parameter, okay, we have n different behavioral sets. So because for each of the observable j, you have a cumulative distribution of x associated to the best fit of j. Okay, so this means that you have a Monte Carlo sample with all your parameters randomly drawn at the same time and all the entire set of observables. And then within this, let's say, individual Monte Carlo sample, you analyze one by one the observables and what drives the best fit for each observable in turn, without doing any extra, let's say, smoother or k-step ahead prediction. Okay, so then in this way you can find trade-offs, because if for two different observables, the Monte Carlo filtering identifies parameter I to be relevant, and the cumulative distributions that fits best observable J is different to the cumulative distribution for which observable K is fitted at best. This means that there is a trade-off. Okay, so now I give you some example of the plots. So again, on the Lubick short-finder model. Okay, this is what happens if we draw from the prior. Okay, so for example, we see that there are quite important trade-offs for a couple of Taylor rule parameters. This is the Taylor rule inertia, and this is the weight to exchange rate in the degree of exchange rate targeting in the Taylor rule. So here you see that so each of the thick lines are cumulative densities of the best fit for each of the observables. So which means that to fit well the exchange rate, we would like to have a higher response, okay, to the exchange rate. But at the same time, this would screw up the fit of interest rate and inflation, because the good fit of interest rate and inflation would actually prefer to have a lower degree of exchange rate targeting. Okay. Second thing is about interest rate inertia. Okay. And here we get a kind of a typical result, because typically quarterly inflation is very volatile, whereas a quarterly interest rate is a very smooth, is a kind of smooth, let's say, series. So then, okay, one trivial way, okay, to fit a smooth series is to have a high persistency. Okay, so then to fit well interest rate, you might want to have a high persistency, a high inertia, but this actually has a trade-off, because actually inflation would prefer to have a smaller persistence of the a smaller inertia in the interest rate. Another interesting thing here is about terms of trade. Okay, you may not remember, but in the Lubick Schoffider model, terms of trade is a purely exogenous process. It's an AR1. Okay, it's an AR1. Okay, so then the yellow line is a very narrow, okay, band that is essentially tells you what would be the OLS. So if you would estimate a pure OLS out of the box of an AR1 process of the terms of trade data, you would get a persistence of 0.3, more or less. Okay, but if instead of, so that would be, this is also a typical strategy, you know. So if you observe exogenous variables and you want to be faster, so what you do, you estimate an AR1 out of the box, you calibrate the parameter to the OLS, so to 0.3, and then you fix it and you estimate other parameters. But since the reduced form, okay, of the linear rational expectation model changes according to the persistence of exogenous shocks, so then it might change also some covariance or autocovariance of other observables. If you estimate the persistence of the shock together with all the other observables, you see that in fact you would like to have a higher ρQ, for example, to fit better the exchange rate. So that's why, and this is the gray line, so which I report here for convenience. So when you estimate, you get actually a higher persistence for the terms of trade with respect to the OLS, exactly for this reason that the reduced form solution provides a different, let's say, covariance structure and autocovariance for other observables, and then you move away from the pure OLS of the individual series. A second comment is that, okay, another comment we can have out of these plots is that, okay, so without doing extra analysis and time-consuming analysis, you may already anticipate that, assume that you remove interest rate data from the data set, most probably you will get smaller inertia in the Taylor rule. Okay. This is not necessarily desirable in the sense that, okay, in general, in my work, I tend to, I mean, if I have, I tend to use all the observables that I can possibly find, but this is something that might be useful. And second, is not necessarily easily, let's say, to fix this, because, I mean, the Taylor rule is like that. Then there is a Phillips curve. So this might possibly tells you that there might be a misspecification on the model, maybe a different Phillips curve, different preferences might attenuate this trade-off. But in this case, it's like just a radiologist, or I mean, just a diagnostic, okay, that says there are trade-offs. And this just tells you why your posterior goes in a different direction, but not necessarily tells you, I mean, the solution on how to get a better fit of inflation or something like that. But it might still be useful to know that there are these trade-offs, because then, I mean, you understand why in the end, I mean, you hoped so much with a nice extra channel in your model to fit better inflation, but then I mean you realize that there is another observable that doesn't like the same feature, and then in the end the posterior doesn't really go where you expected ex ante. Okay, these are other examples. Okay, there are other types of plots where, okay, so the plots are organized by parameter or by observables. So when for the plots organized by observable, you see for all the parameters that let's say are relevant for interest rate in this case. Okay, so here you see that for the interest rate there are 3 parameters that might drive its fit. So then, okay, if you wanna push you're desperate, I don't know, and you wanna marginally improve the fit of interest rate, whatever happens to the other variables, okay, you lower a bit psi 3, you increase rho r, and you increase rho is, and then I expect that the fit of interest rate improves, but maybe completely screwing up the rest. But okay, that's what it says in this plot. Okay, there are also these other kinds of things. So again, in the diagonal and then the off diagonal, and as I said, I mean, typically, and we all know that estimation is very difficult. And clearly, I mean, if you observe 5 variables and you just want to improve the fit of one, clearly, I mean, it's difficult to pin down. I mean, easy combination of parameters that makes the thing happen. Probably it's more interesting to do the same, or it can be interesting to do the same in the posterior, because then, okay, as I said, this is a situation where you have your model, you are happy with him, and then you have a lot of hopes and let's say ambition that it will fit super well everything. And maybe it's not the case for everything. And then, okay, this tells within the posterior distribution whether there are trade-offs. And similarly to before, no, there are trade-offs, for example, between inflation and interest rate for the inertia, with the same quality. So, I mean, if you move low within the posterior, you improve the fit of inflation, but you deteriorate the fit of the interest rate. Similarly, for the interest rate response to inflation, if it is smaller, you fit better inflation, but you would deteriorate the fit of the exchange rate. Other things for the degree of openness. So less openness seems to suggest a better fit of GDP, but more openness would fit better exchange rate and prices. Similar plot for ROQ, the AR1 versus the simultaneous estimation of ROQ in the presence of other observables. And okay, this is triggered by RMSE option. Sorry, the quality is horrible of this table. And where you can set the p-values for the RMSE analysis. Okay, that's all for let's say let's call the lecture. So and okay, some comments and caveats. So we started the discussion emphasizing that sometimes we really want to address a global sensitivity, in the sense that you are really have your parameter are not so precisely pinned down, that you can just take a derivative, and the model is nonlinear. So you want to really propagate a substantial amount of uncertainty to your model and trace it out from the output behavior. And so that's why, in general, that's when you need the global sensitivity analysis. So, and then for triggering this, you need to vary all factors, all parameters at the same time in a Monte Carlo fashion, to trigger all the nonlinearities, to trigger all the interaction and everything, which makes the propagation proper, but also makes the problem difficult because it's a nonlinear inverse problem. global sensitivity analysis, sorry, regional sensitivity analysis or Monte Carlo filtering is a very simple way to tackle this problem. It is very effective in many applications. Yeah, I mean, we could pin down many, I mean, issues that drove me crazy in the years with this very simple criterion. But you need to know that it is based on, I mean, simple univariate and bivariate projections of k-dimensional things. Okay, so then there might be high order interactions that we are missing. So, which more formally means that this is a which means that the sensitivity test of Monte Carlo filtering is a sufficient test, but not necessary. It means that there might be nasty problems where RSA doesn't identify a parameter, but in fact there is a seventh order interaction where a parameter apparently irrelevant matters. So this you need to know. I have also to say that in practice, then I mean, okay, you might miss some higher order element, but in practice, it always helped me in my life in my work. Okay, life is a different thing, it's a more serious thing. In my work, to pin down, I mean, relevant things. But okay, you have to be aware that this is a sufficient condition and not necessary. Yeah, okay, it is written here. So there are other more important, other more complicated pattern recognition methodologies that can be used. They are not available in the NR. In principle, okay, if you really have complicated problems you want to analyze more in detail, okay, there are other non-parametric tests, non-parametric approaches that you can apply. Okay, I make a bit of a little pause. I drink some water, and then, if you like, I can start showing some MATLAB, let's say, examples running, and see how they go. In the meantime, if there are already some questions or concerns or whatever. Okay, I hear somebody. Ah no, there is something. Okay. Allora, when explaining slide 65, okay, when explaining this, you have said that this is used for nonlinear model. Does it mean that the agnostic is not necessary if the model is entered as linear? As I said, the general response is no, in the sense that it depends whether there is a non-linearity in the linear form, in the linearity on how the parameters enter. Okay, so for example, even the Metzenbacher's model is a model linearized by hand. Okay, it is implemented linearly, but the deep parameters enter non-linearly. Okay, in the Metzenbacher's model, especially in the reduced plot solution. So in general, the response is the diagnostic is useful also for linear or linearized models, as soon as, so what I mean, linear in the endogenous variable. The model must be non-linear in the deep parameters, and this is the case in almost all DFG models. Okay, so that's why in the end we apply these nonlinear techniques to linearized models, because the model is only linear in the endogenous, but not linear in the G parameters.
Excuse me, I have a question, please. The sensibility analysis is done only on stochastic model, or can it be done on both stochastic and deterministic model?
Okay, it is triggered only in the stochastic mode. Okay, then okay, if the problem is Blanchard-Kahn violation, it doesn't matter, because either deterministic or stochastic, Blanchard-Kahn conditions are the same. So if the Blanchard-Kahn, so the Blanchard-Kahn condition analysis on the stochastic model applies identically also to the deterministic model. If you want to do a sensitivity analysis for example, deterministic simulation of anticipated shock and for perfect foresight, there is no kind of interface to do that. In principle, then you might have to do by your own the Monte Carlo draws and then apply out of the box. So then in that case, what you would do, okay, you do it maybe on the linear simulation for the stochastic, you do for the simulation, the stochastic simulation, and then you try to apply the result to the deterministic one. And okay, if the model is not too nonlinear, you might already have something useful.
Okay, thank you.
You're welcome. Then Diego De Souza. I mean, in case I have fixed parameters, can I give a range for and do the test? Okay, can we apply this model only for the case in which we have... Yes, okay. Not sure. I think you need a prior, because okay, for the identification, okay, we allow also to test all parameters now without having the prior. I think that here you always need a prior. So you need at least you don't have to be very precise on your priors, of course. It can just be uniform within a range, and yeah, because otherwise, I mean, you don't know the space on which to draw, because you need to do a Monte Carlo thing. So you must tell Dynar in which domain you want to sample your parameters. Okay, so so maybe I can show you a couple of, but as I said, I mean, if you have questions, just tell me. And then, okay, there are also the Q&A sessions as well. I show you a couple. I mean, I ran some MATLAB, some Dynar instances, and show, I mean, some hands-on performance of the thing. So let me. This is okay. I share my screen and I pick. I hope. The proper MATLAB. Okay, so let's start with the. I hope you see MATLAB. So So here is an implementation of the Neo-Keynesian Phillips curve. So we have the cycle and the Phillips curve with the omega. Okay, so the very first example that I showed you. As I told you before, I mean, if you just want to explore things, you don't need to be precise. You just list some uniform priors and you check what's happening. I think that Dynair also requests you to declare an observable, although it is not used, because in any case, since I mean the sensitivity toolbox kind of let's say leverage on top of the estimation structure of the model due to this prior thing. So Dynair also expects an observable, even if in the end we are not using this information. So even if you don't have the data, even if so here there's no data set, there's no data set in the directory. So but it's just enough that you declare whatever endogenous as an observable. Otherwise, you get a crash. Okay. So then, what's happening if you do Dynair and K1? It starts Monte Carlo iteration. Probably you just see a gray window here, or even nothing. I don't know. There is a bar that progresses, and I fear that you don't see figures, right? So then let me dock them. Do you confirm? Can someone confirm that you don't see the figures?
No, we don't see them.
We don't see the figures.
Okay, thank you. Now you see them?
Yes, yes, we see them.
Okay. Okay, so that's the way to do it. Nice. Okay, so so you remember that the stability, the uniqueness of solution was omega smaller than 0.5, and that's exactly what is told by this plot. And the second is that we had 3 parameters, but the p-value, the significant p-value is only for 1 parameter. So Dynair directly plots only the parameter that is significant without I mean, plotting things that are useless. So this tells that omega has to be smaller than 0.5 to get a unique solution for the super small, super simple Phillips curve model. Okay, and then within the no saddle path, in fact, what you get is that whatever else happens is an explosive solution. So there is an excess of explosive roots. And for this simple model, that's all you can say about saddle path, the saddle path things. Okay, so now if I close all, okay, fine. So now there is the slightly more complicated version where you have omega b and omega f, and we run again. Sorry. K2. Okay, you don't see there is a bar that progresses, Monte Carlo. Okay, do 2000 iterations, could be less than them, but 2000 is the default. So typically for large models, I would go for a couple of hundreds. Still you get something. Useful. Okay, so now I dock again all the figures such that you can see them. Okay, so that's the. Maybe I make it a bit smaller so you see better the dots. So that's the main graph that I discussed earlier, and so we see that there is this So omega f plus omega b must be smaller than 1. So the low triangular part is perfectly identified by the Monte Carlo filtering. Okay, so that's what this plot tells. Then if you go to other figures, where are the other figures? Oh, okay. I have to restart MATLAB, I think. No, okay, let me speak. So this is indeterminacy. So indeterminacy, you have it when in this triangle here. So where omega b is between 0 and 1, but omega f is above 0.5 and in this portion of space. So then explosive solutions, we need to look here to have the same notation. So it's in the other part of the triangle. So which means that this red part here is divided in two portions, and one is indeterminacy and the other is explosive. Solutions. I think that I have to restart MATLAB. So sorry. So I restart MATLAB and I go for some Lubick short-file model to show some. Reopen it. Sorry, I have to open another instance. Okay. Okay. Okay, I share again. Share again. This one here. I think we are back. Okay. Okay, this is the Lubick short-file model. This is also used in many test cases of the Dinard distribution. Going back to the previous questions, as you see, the model is linear. Okay, but the parameter, okay, enter directly non-linearly, but then furthermore in the reduced form solution there are further degrees of nonlinearities. And so that's why even if the model is linearized at end, in the end the mapping between the D parameters and the behavior is still nonlinear. We plug in the Lubick short-file priors and we do some sensitivity analysis. So the first one is just the Blanchard-Kahn. Okay. Then we do root mean square error analysis. So we map the fit, okay, using the prior. So how to do so? So you need to have a data file. You need to declare first obs and obs per filter. So all these things that you need to do for estimation, as for example, Johannes has very clearly explained to you. And then, okay, since you did already sensitivity, you can just load the previous sample. You don't do again the stability mapping because you did it already before. You do RMSE equal to 1. And then, okay, this is a sort of a pre-sample. So you ignore the one-step ahead prediction in the first period. because it's a bit trivial, because in the first period the one-step prediction is just the unconditional mean of the steady state essentially of your model. Okay. Then I estimate the model, and then I do some neighborhood around the mode, neighborhood exploration, and some other stuff on the posterior. And finally, I also do on the posterior. The last thing I do is that on the posterior. So I showed during the lecture how to do this IRF calibration on the prior. You might do also the same on the posterior, and so I can show you also a further example of this. So let's run this. Okay, actually, or maybe I directly show you the results instead of running it, because in the end you need to learn also how to browse the results. So you know that Dynar generates a directory with the same name of the mod file that stores all the results. So, and then if you do sensitivity analysis, there is a GSA, Global Sensitivity Analysis subdirectory, which stores a lot of things. So for this model, we did, sorry, I didn't want to do this. So maybe I do directly here inside. Okay. So so we did a lot of things. We did some prior, so stable, it means where the stable suffix means Blanchard-Kahn condition from the prior. Okay, and here we recover by doing so, here we recover the same plot in the presentation. Okay, so the generalized Taylor principle. You see that we have a unique solution if the sum of psi1 and psi3 is above this line. So essentially, psi1 plus psi3 bigger than 1, generalize the Taylor principle for exchange rate targeting. No, we want to go here. Okay, then and then Dynar also checks what happens in the red zone, and in this case it only founds indeterminacy. So when we are red, the only thing that can happen is indeterminacy. There is no explosive root, the steady state is always computable, nothing goes wrong. Also because the model is linear, so the steady state is always computable. Then we have the root mean square error analysis. We do it from the posterior, we do it from the prior. So for example, we can look for example, for each observable, for example, for interest rate, all the parameters that matter for the fit of interest rate, which is, I think, also one of the plots that I showed you. So it means that there are 3 parameters that are mostly involved in these trade-offs, and then there is a trade-off with inflation when we talk about interest rate inertia, and there is a trade-off with exchange rate when we talk about the degree of exchange rate targeting. You can also, so then the plots are done by observable and by parameters. So then you can also have all the parameters, and for all the parameters we plot the lines corresponding to the relevant observation. So then you know that we know here that for psi3 the issues are between R, pi ops, and the exchange rate. For OR, the trade-offs are between interest rate, inflation, and exchange rate, and so on and so forth. Okay, so then you can, sorry, you didn't see the figure right here. Okay, so then for each parameter, we plot all the relevant observables and distributions, and cumulative distributions. What else? Okay, right. Then we have these Monte Carlo filtering plots for each observables that are kind of very difficult. I mean, you find very little blue, no? So it's difficult just to improve the fit of inflation, just moving one parameter alone or a couple of parameters together. You really need to do a formal estimation and optimize everything together, because I mean the fit of inflation is driven by simultaneous cooperation of many parameters. But for example, if you go to the terms of trade, that, as I said, is a purely exogenous variable. For the terms of trade, vice versa, I mean, if you want to fit at best terms of trade, you do the OLS and you pick something like 0.25. You don't see. Sorry. You don't see. For the terms of trade, the Monte Carlo filtering only pins down one parameter, which is the persistence of the AR1. The persistence of the AR1, and yeah, that's essentially the OLS result. Okay, there is also another way to draw parameter samples, which is Monte Carlo. So this is a way. So instead of making a metropolis, you draw multivariate normal around, so using the intersection around the posterior mode. So in the end, okay, maybe this is a more rare situation, but just for you to know that you can also draw with a multivariate normal around a specific point in the space. If you want to do so, okay, you can do similar analysis, and yeah, that's it. So then you can sample from the prior, and then prior range 1 or 0. So if you want a uniform or really, let's say, honor the prior distribution, you can draw from, you can pick posterior draws from Metropolis Markov chain Monte Carlo, or you can also pick multivariate normal around a specific point in the parameter space. Then, okay, we saw in the lecture IRF moment calibration from the prior. Now I show you something about, I think is, yeah, if I remember well, no, it's another one. Yeah. Okay, so, come on. Okay, so you know that, or maybe you don't know, but okay, you will learn at least at some point. You might have learned that okay, when you estimate a model with Bayesian methods, you also get posterior distributions of whatever you like. For example, you have the posterior of the IRFs. In this case, there is one IRF, the IRF to the rest of the world inflation. That you see that on impact entails a huge uncertainty. You see that the interest rate response on impact, I mean, is most of the time negative. But can also be positive or very near to zero. So then one may be curious to see within the posterior. So then this also means that this IRF is not very well identified, in a sense that, okay, it's not very clear what's the let's say, likely response on impact of the interest rate. So one may be curious to understand what's happening. So what I do, then I pick the IRF on impact, so first period of the IRF versus the shock to the rest of the price. And then, for example, I check what would drive this IRF to be kind of small in absolute value, no? So here you can really read the numbers on the y-axis. So my range is a range that starts from minus 0.05 and arrive to something positive. So I want to exclude too big. I mean, it's a way to detect what's happening. So so let's see what happens. What drives this to be small, and then the complement, of course, is the other thing. Okay. So then we go again to the folder, and we open. You see there are IRF restrictions and IRF calibration. So there are two types of plots that I also showed during the presentation. So one is let's say just a visual representation of your restriction. So this is the cumulative distribution of your in the posterior of this impact response of interest rate versus the rest of the world inflation shock. And this is the blue. The blue is the area for which I want to filter. So this is my filtering criterion. Okay, this is also kind of okay. This is also kind of to check that I mean you have implemented correctly your criterion for filtering. And then the other type of plot is the result of the sensitivity analysis. So we open it, I hope, yes. And that's, and by the way, I mean, they are very artistic plots. You can hang on in the living room. Joking, sorry. Okay, so we see that so on the diagonal first, no? So so this tells that large values of the persistence of the shock triggers smaller response of the interest rate. Smaller degree of exchange rate targeting also triggers less response of the interest rate. Higher slope of the Phillips curve also triggers smaller response of the interest rate. And if you go to the lower triangular, you can pin down some clear, let's say, patterns. So if you combine high persistence with the small psi 3 and high kappa, you probably go in a situation where the response of interest rate is actually smaller. Okay, maybe I can try something I should never try, but I always do it. Maybe we could check it kind of on the fly. So whether we can indeed so we load the mode. Okay, let's load the mode. We load the mode, and then we do set all parameters. Y I just wanted to check. Maybe in the Q&A I do it by my own. Otherwise, I mean, it's a bit difficult to follow. Okay, there is the other example here of what I showed in the lecture of this moment calibration. So here I have re-implemented, okay, actually, this is a bit sloppy because, okay, now Linar has properly implemented all the options. So relative IRFs is an option of IRF calibration. And so this implements exactly what happened in the presentation. And so you may run it. Run it. All right, it's not in the workspace because I didn't run. I think. Okay. Anyhow, it's amazing that I mean, if you follow the suggestions of those red and blue plots, I mean, normally you get what you want. So. But sometimes it really helps you. So first checks the Blanche Arcane, and then starts also checking the prior restrictions. By the way, on the screen, we also plot the p-value. So as I said in the presentation, the parameter is important. The smaller the p-value, so when you look very small, I mean, a long array of zeros, it means that, and then vice versa, the Smirnov statistic is large, of course, no? Because then it means that the two cumulative distributions are very distant to each other. And yeah, so this is the first thing it does is prior restrictions altogether. So all the RFs and all the moments. And then compute all the things individually. Prints the results on the screen, makes the plots in the subdirectory, and yeah, that's it. So for example, you see that, okay, to match interest rate versus YS shock, it is relatively easy at period 29. Now, as I said, one by one, it's easy. If you put the more constraints you put together, the more it's difficult, of course. And okay, it does it for each and every restriction, so it takes a while. And then in the end, you have, I mean, you can really pin down each and every element of the puzzle. Okay, there is an hand raised, please.
Yes. I have just one question. Can we set as much as restriction on the IRF as wanted?
Sorry?
Can we set how many restrictions can we set on the IRF? Like, is there a limited number?
Up to infinite.
Okay.
In principle, you can really put whatever. Of course, I mean, it is more and more difficult to pin down all of them simultaneously. So okay. In a way, you can see this as a brute force optimization, in the sense that you just draw randomly parameters and you pick the combination that, okay, that matches all the restrictions. No, clearly, I mean, this is the most the less efficient, let's say, way of optimization, but at the same time, I mean, if you want to, it provides you quickly some most of the time interesting and useful suggestions.
Okay, thank you.
Okay, moments, and then okay, it finishes. Okay, maybe I quickly, okay, that's just the end. Okay, and then again in this ILS 2003A, we have another set of results with all these plots, plots of the calibrations. No, so it says so here. Yeah, this is the very same plot I have in the presentation. So this is the black lines show, let's say, the domain, so where your Monte Carlo draws go, and then the blue area is where you want to focus on with your filtering. And then there are all the other results. So these are, so you know that for moments Y versus pi, there are these 9 moments. So you can look at them one by one or all of them. And yeah, so here you have that okay, combination of smaller rho R and larger rho A would provide that kind of co-movements between inflation and GDP, for example. Yeah, so that's more or less how it is. This is the same thing for the moments. So then you can see, so you can compare, the outcome of your Monte Carlo, draws depicted by the black lines with your, let's say, criterion. Okay. Yeah. Okay, maybe I just tell you a couple of notes on the exercises, on the exercise that I posted, if you are willing to try them. And they are structured in a way close. Where is it? Okay, sorry, I have to open it. Problem. So I opened the Word document, now I share it. Okay. I hope you can see it. Okay. So this set of examples tries to kind of put you, okay, in situations where you need the toolbox. Okay. So there are a number of files that bring you, for example, to Blanchard violation. And maybe also some errors in the call. And then, okay, there are variants. So then okay, so there is a first Blanchard violation. Then determine whether in a neighbor of 10% around that special mode Blanchard conditions are satisfied, or vice versa, increase the neighborhood. Okay, so try to see, I mean, step by step, how you can, for example, you just put together a first version of a model, you calibrate your parameters, you want to see some IRF and you have Blanchard-Kahn violation, and then you start going crazy. I mean, tilting the parameters to get the unique solution. This puts you in this situation, and then how you can use the toolkit to move your parameters in order to get proper parameters for the simulations. And yeah, things like that. Then estimate the model. We check Blanchard-Kahn simulation, IRF, calibration, and so on. Moment, correlation. Okay, so it's a bit of a guided things, and then I will post tomorrow or tonight the solution. I mean, so to get a bit of thrill if some of you really want to practice. I mean, otherwise you can practice whenever you want in the future when you realize that you might need this stuff here. Okay. I think that's it for the moment. Okay, I thank you for attending. Okay, there will be then Q&A later today and tomorrow morning. So there are no immediate questions. I would close the meeting. Otherwise, please post on the chat or raise your, I mean, just open the mic and make the question. Okay, so I think that nobody, so I think we are all tired. We need some drink or food, I guess. Okay, so see you later. And in any case, I hope you enjoyed and you will enjoy the remainder of the course. Bye-bye.
Thank you, Professor.
Bye-bye.
Bye-bye.
Thank you very much.
Bye-bye. Thank you. Thank you very much.